do the thing. All right, so for Friedel-Crafts, we have alkylation and acylation. And does someone want to remind me what the reagents are for alkylation? Yes. Let me actually. Cool. And so RX is just a alkyl halide, and AlCl3 is our Lewis acid. Cool. And then when can this reaction not occur? Like, what were the limitations that we talked about? Yes. And not if strong deactivators or what? So it cannot happen if strong deactivators or NH2 are on the ring. Awesome. So what are the reagents for the acylation? Yes. So I'm going to do it over here. Happen? We are going to go over that because we didn't get to do that in SI. And again, AlCl3. So what are the limitations for the acylation? It's exactly the same. Ta-da. And then for the alkylation, we talked about two things that only happen with alkylation reactions. Does anyone remember what that was? Polysubstitution and rearrangement. And why do rearrangements happen? Because there's a carbocation. Cool. Okay. So is everyone good? We remember this stuff? If maybe. Okay. So I will zoom out just a tad so you can see this. And then we're going to do some practice problems for alkylation. Did you guys have like the rearrangement question on your exam? Okay, so maybe some people had it, some people didn't. I think it'll show up on the next exam. So we're going to practice it anyways. So just, I guess, the simple, straightforward ones that we see here. Dr. West went over this one in class a couple times, but basically for an alkylation, what we're going to do is we're just going to chop this off and add a plus charge. So we get 1, 2, 3 carbons plus charge. And as we said, we can do a rearrangement. So we would get this because secondary is more stable than primary. And then basically, instead of doing the entire reaction mechanism every single time, what I want you guys to do is just draw out the benzene ring. And if there's nothing on it, you can just add this group right to the chain anywhere you want. So we're going to say 1, 2, 3. All we have to do is make sure that we attach to carbon number 2. Ta-da! I kind of did it the fast way. Does anyone have any questions about how I got here? Yes, if there's nothing on the benzene ring, you could put this anywhere you want. Yes. Okay, not a stupid question whatsoever. A lot of people get tripped up on this. So basically, our carbocation has 3 carbons, right? And this bond is just forming from one of the carbons of the benzene ring to the carbon number 2 in the carbocation. So what's going to happen is the hydrogen that was here is going to get taken away. So no, we ignore the hydrogen. That bond is purely just carbon to carbon. All right. So we haven't gone over like multiple substitutions, activators, deactivators, or anything. So I'm going to wait to do a couple of these. But the one that I really want to show you is this guy. I think we did it super, super briefly in the exam review or something. But essentially, what we got to do is we're going to cut off bromine, and we're left with a box, a plus charge. And what kind of rearrangement could we do here? Ring expansion. What were you going to say, Eric? Okay, so that's a really great point because this right here would be a tertiary carbocation, right? So that would be pretty stable, except these cyclobutane rings are really, really crappy. We do not like them. They're super unstable. So the instability of that ring kind of beats the stability of a tertiary carbocation. So what we're going to try and do instead is a ring expansion. And I'm going to show you the long way to do it, and then I'm going to show you like just know the product kind of thing, because I know ring expansions were from Orgo 1, and that was a long time ago. So I'm going to go ahead and call this carbon 1, 2, 3, 4, 5. And what I'm also going to do is first going to draw out the hydrogens for you. So we have one hydrogen here. Since it's a plus charge, we only have one. We have one hydrogen here. 2, 2, 2. Now again, 1, carbon 2, carbon 3. 1, 2, 3, 4, 5. So when we do a ring expansion, we're going to break this bond right here. And we're going to attach this carbon to the cation. And so when we redraw it, I'll make this carbon 1. Get a 5-membered ring. So this will be 2, 3, 4, 5. On carbon number 1, we have a methyl. And we also have one hydrogen. Cool. So carbons 3, 4, and 5 each have 2 hydrogens. And carbon number 2 only has 1 hydrogen. So what carbon is the cation going to be on? Carbon number 2, because it's missing a hydrogen. Cool. So that's basically how you would do a ring expansion. But the way you can just think about it is if you have a 4-membered ring, have a plus charge that's like 1 carbon away, all you're going to do is make a 5-membered ring. Wherever your substituent is, plus charge goes next to it. Just because I like to do, if I'm making a 5-membered ring, I like to just count to 5, and then whatever's left over, I leave it as a substituent. Okay, great question. So the reason you can't have a 6-membered ring is because when you're doing a ring expansion, you can only expand like 1 carbon at a time. And then the next question that people always ask me is, well, then why can't we do another rearrangement to bring this carbocation here and get it to be tertiary? In this class, we're only doing 1 rearrangement at a time. So only 1 ring expansion, or only 1 methyl shift, or only 1 hydride shift. We can't do multiple things. So that's why, again, we would stop at a 5-membered ring instead of maybe making a 6-membered ring. Sense-ish? Okay, cool. So then now that we have this sort of ugly looking carbocation, let's draw what the final product would look like. I'm going to do that right up here. So we have a bond, and that bond is going to go to carbon number 2. And we know that on carbon number 1, which is right next door, we have a methyl. And I'm just going to move this over because it looks. So how does this feel? like that sometimes. Great. Okay. So, any questions on this? I don't know if I already asked you that. Okay, cool. So let's go on. We're going to come back to this one after we talk about activators, deactivators, things like that. So again, just in case anybody missed it, when we're talking about a benzene ring, we can have any substituent. I don't know why I put G here, just because anything, I guess. But the position right next door to that substituent is called ortho. One more away is called meta. This one right here is called para. All right. So now we're going to talk about activators, deactivators. I know you already did this in lecture like a week ago, but I do want to cover it again with you guys. So, okay. People have heard the terms meta deactivator, ortho para activator, meta whatever. But what I want you guys to think about right now is ortho para director, activator, deactivator. Those are two separate things. So first we're going to talk about what's an activator, what's a deactivator. And then we're going to talk about what's ortho para directing, what's meta directing. And right now we're going to treat them as two completely separate things. All right. So the difference between an activator and a deactivator is simply how does it make the benzene more or less reactive. So I'm going to draw a benzene. Actually, I'm going to make myself a new page. As I do. I don't know why I make these handouts sometimes. All right, so benzene right here. And what do we know about the reactivity of benzene? It's super stable, so it really doesn't want to react, right? And what else do we know about benzene's role in an electrophilic aromatic substitution? It's a nucleophile, cool. So we're going to just start out with that, right? And so if we say that something is an activator, we're going to make it more reactive. So I'm going to draw, or I'm going to write, I guess, activator on this side. And then deactivator is going to make the benzene ring less reactive. And so when we think about like past chapters with donating groups, drawing groups, this and that, especially think about Diels-Alder reactions, what makes a nucleophile more active? What? Could be, yeah, depending on what kind of reaction we have. That's true. Electron donating groups. Yes, so I think you guys are all on the right track. But the big thing that we want to take away is electron donating groups make nucleophiles more active. So I'll write that down for you. Electron donating groups make nucleophiles more reactive. And why is that? There's like a million different ways you can phrase it. So what do you guys think? Yeah. Yes, exactly. So basically, electron donating groups are giving the nucleophile more electrons. And the more electrons it has, the better of a nucleophile it can be. Cool. So then the opposite is true for, what do you mean? Okay. All right, hold on. It stopped sharing, even though it doesn't look like it did. Give it a second. Monday. Okay. Share, please. There we go. Spoke too soon. Yay! Okay. Well, luckily we do have a whiteboard, but I don't want to use it, so let's hope it turns on. Webex wants to sign in. Yeah, bro. Like, okay. Nope, don't start video. Just start sharing, please. Life is so hard. Stop sharing. Webex, you have like 10 seconds to get it together. Come on. Believe in you. Haha! Nope. Okay. Shut up, Webex, please, for 1 second. End meeting. Okay, this way I can still record it. Shut up. Okay. Dr. West. What? I have my tea. I wish I had a sippy cup. I absolutely can't. I would love to be a Kiwi. I don't know if anyone's been to Dr. West's like real life office, but he has a Kiwi sticker, like straight up like off of a Kiwi, like a produce sticker on his door. And it makes my day every time I see it. I'm like, yeah, Dr. West, you go. Right? Right? Okay. So redo, restart. I hope the other recording stays. Is it still recording? WebEx only records when you don't think it's going to. All right, so let's redo that last little bit. I have a gigantic scrunchie, don't mind that. I have no concept of how big I should be writing, so if you can't see at some point, let me know. All right, benzene, cool. We have the activators, which we just talked about. I'm not going to rewrite the whole thing that I did. I'm too dyslexic for this, bro. Come on. Does anyone want to tell me how? Right backwards. You know, if I could, I would. I think that's autofocus. Hold on. We can make a plan B if this doesn't. That's a lot. It's already 11:30. I'm just gonna take one for the team and suffer and try to use this. Open. Huh? But then I can't record it and people get upset. Okay, I win. It's working. It's working. Hey, that's true. Oh. You guys are gonna see me cry now. Just work. Okay, thank you. All right. That was aggressive. Benzene. Woohoo. Okay, so does anyone remember any of the electron donating groups? Okay, cool. R groups. One. Wait. The next thing you touch will be a right click. I don't want that. Like, why would I want that? Whatever. I guess fuck the online people. Leela, can I borrow one of your markers? I give up. I really do. I really do. What? Just type. Whatever. Yeah, okay. Yeah, we do have 30 minutes. Maybe we'll just have a conversation about it. This is fine. Everything's fine. Okay. Let's talk activators, right, guys? So activators, the best activators we have are ones that have lone pairs. Because lone pairs donate right into the nucleophile. And what are some lone pairs that we know about? OH, cool, and the other. Okay. Sorry, this just. That will be plan E. we're already close. That's all right. Okay. Okay, so yes, activators, lone pairs. I'm gonna write lone pairs. And the strongest activator that we have is NH2. And then after that is OH. And then someone else also mentioned the ester groups. So does the ester, in order to be a donating group, does it have to be attached from the oxygen side or from the carbonyl side? Oxygen side, cool. So we can have esters, and we can also have, what are these guys called? Amides, cool. So esters and amides. And then what was the last thing we talked about? Someone said it before, like the weakest donating group. Carbon chains, yes, so we have R groups. All right, so for deactivators, we want electron withdrawing group because it makes the nucleophile less reactive. And does anyone remember any deactivators? Halogens, okay, cool. That one is kind of okay. I think the one that would be better to use is CBr3 or CF3 or any of the halogens. What else? NO2. What was it that you said? Yes. We also have SO3H. We also have carbonyls, yes. So we have esters, ketones and aldehydes. And then we also have esters and amides if it's attached at the carbonyl side. This is a pretty good list for now. Does anyone have anything else they want to add? Yes. The R group. Don't worry about it. If you have multiple rings, there's going to be a reason, and we're going to talk about it. But all right, so does everyone kind of understand what's the difference between an activator and a deactivator? Exactly. Okay, cool. So now we're going to talk about directing effects. And so with directing effects, we're going to have ortho-para-directors. And we're going to have meta-directors. And in order to really understand these guys, we're going to pick 3 different substituents, and we're going to look at the resonance for them right quick. And since we kind of wasted a lot of time, I'm going to just cheat, and I'm going to show you the resonance I already drew out. So the first one we're going to look at is the alcohol, and we know that the alcohol is a what group? Donating group. Cool. It has a lone pair of electrons. Awesome. So when we do resonance, we donate those electrons into the ring, and we do resonance all the way around the molecule. And what's important to note is that the charge that goes around the ring is what? Negative or positive? Negative. Cool. So that negative charge that forms during resonance on the ortho and para positions is going to give you a delta minus on the ortho and para position. So that means if we have an OH or some kind of substituent like OH, hopefully that's easier for you guys to see, we're going to end up with an extra negative charge on the ortho and para position. So the next group will add ortho para because those are the most nucleophilic spots. So I'll repeat, the ortho and para positions are the most nucleophilic spots. For now, no, we're going to forget about steric hindrance. Yes. Yes, so when we do resonance around the ring, we essentially end up taking this double bond, donates ortho. We do resonance again, we get a negative charge on the para position. Then again, this forms a double bond, this double bond knocks up here. We end up with a negative charge on the other ortho position. Yes. Yes, so if I understood your question correctly, you're basically asking, like, does it matter what this substituent is? And yes, it absolutely does. So any of the electron donating groups that we talked about will do resonance like this. Besides R groups. So R groups don't actually donate electrons through resonance. They donate through what? Electronic effects and inductive effects. Awesome. So all of the donating groups are going to do this, except R groups, and that's why we consider R groups really weakly donating. They're still donators, they're still ortho-para directors, but they're really weak donators. Like if you made the negative charges, double bonds the opposite. Oh, wait. I think you mean like, isn't this and this exactly the same? Yes, but that's kind of the point of resonance. So it is exactly the same. The only thing that changed is where the electrons are. That's something that also really messed me up, especially with the cyclopentadienyl cation or whatever it is. When you do resonance like all around the ring twice, even though it's like the same exact molecule. All you have to know is that these guys aren't even real things, like these structures, it's just a way to depict the molecule. So yes, it is exactly the same. All it's showing us is that the electrons can move all the way around. Yep. All right. Now the second thing, also, I lied. We're going to go back here to the notes. And what I want your main takeaway from that to be is electron donating groups form negative charge on the ortho para positions, and that makes them more nucleophilic. One moment. Talk about that. All right, so I will come back to this page in a second, but I do want to show you. So ignore the fact that it's called ortho-para deactivator. We haven't talked about that yet. But let's say we have a halogen, right? So halogens are weird in that, do they donate or do they withdraw? They're withdrawing groups because they're super, super electronegative. They're stealing all this electron density. But they have lone pairs. They don't like to donate their lone pairs, but theoretically, if we were doing resonance, this is how we would draw it out. So even though this is a withdrawing group, it forms a negative charge on the ortho and the para position, just like OH did, right? So now this is weird because would this direct ortho para or would we direct meta? What do we think? It's the same exact thing. So we would still direct ortho para, right? Even though it's a deactivator. So I want you guys to just take note that halogens, even though they are donating, even though they are withdrawing groups and they take electron density out of the ring, resonance still shows us that they are ortho-para directors because they have a negative charge on the ortho and para position. Yes. Yes, so if we ever see a halogen, automatically we know it's a deactivator, but we also know that it's an ortho-para director. Versus the next example, which is another deactivator. And essentially, every single deactivator besides halogens are going to have resonance like this. So when we do the resonance, you can already see from this first one, it's backwards because the electrons are going outside of the ring, not into the ring. So we still have a charge on the ortho and para positions. That's just how resonance works in a benzene ring. But instead of a negative charge on these positions, we get a positive charge. So now we still have a charge on ortho-para, but it's delta plus. So if it's delta plus, that means ortho-para is very electrophilic, which means that by default, meta is the more nucleophilic center. Let me just finish writing and then I will explain. So great question. What does that mean? So unlike the two that we did just now, if we were to add another group to this benzene ring, we would have to add them to the meta position. Whereas in the other two, we were adding to the ortho-para position. I'll keep this up for a second, and I want to do at least one example before I let you go, just so it makes sense. Yeah. Yep. Yep. Yes. Exactly. So it's not like the other example when it was extra negative and it was extra good at attacking. It doesn't even want to go on the ring, but I guess if it's going to be added, it prefers no charge to a plus charge. Exactly. So let's go back to the other document. And we're basically going to fill in that halogens are also going to form a negative charge on orthopara, even though they are withdrawing. So halogens are going to have a negative charge on orthopara, even though they are withdrawing groups. And then last but not least, all electron withdrawing groups besides halogens will form plus charges on orthopara, making them electrophilic. Do this little arrow because that's how my brain works. And that makes the meta position more nucleophilic by comparison. And I will give you a minute to write this stuff down and everything. Electron withdrawing groups besides halogens, yeah. There's such little care for my writing and or spelling, so I apologize if you can't read anything. Anyway, I'll leave this up for another second. Show you an example. We have 2 minutes. Fine. Yes. So when you're doing resonance, right, we're going to start with the extra electron, so like the lone pair. And then that's going to make a double bond right attached to it. And then the adjacent carbon gets the charge. So let's say we have this. These electrons go here. And that forms a, no, I lied. These electrons go here. And this adjacent carbon receives the charge. So it's always going to be like wherever you start with the electrons, 1, 2, that one gets the charge. Okay, good question. All right, so let's put these things together really quick. So activator, deactivator, all that means is whether it's making benzene more or less reactive. Orthopara directors are saying that specifically the orthopara position is more reactive. And then meta directors are saying specifically the meta position is more reactive. So we're going to put those things together and we're going to get orthopara activators, which are, I have it written down here. Okay, cool. So orthopara activators include all the electron donating groups and they direct orthopara. They make benzene rings more reactive overall. Orthopara deactivators, these are only halogens. And we call these guys the weak deactivators. Again, only halogens. They direct orthopara and they make benzene less reactive. And then last but not least, all the meta directors include all of the electron withdrawing groups except for halogens. They direct meta and they make benzene less reactive. So for example, let's say we had a benzene ring and it has an OH on it. Overall, is this benzene ring going to be more reactive or less reactive than a regular old benzene? More reactive, cool, because it's more nucleophilic. And let's say we react it with Br2 and FeBr3. What do we add to the benzene ring with these reagents? Just the Br, exactly. So, OH is going to direct where? Ortho or para, cool. So I'm going to draw an arrow to the ortho and para position, right? So the bromine is going to be added to one of those positions. So we can have two products, actually. We can have, we can have the ortho product, or we can have the para product. And I'm not going to draw the other ortho product because they're exactly the same. And the last thing I want to leave you with, I know it's already past 11:50, I'm sorry, but Dr. West says that these will approximately be 50-50. So the ortho product and the para product are going to have like 50-50 mixture. So one is not going to be major and minor. They're going to be approximately the same. All right. I will leave you with that. Have a nice day. If you have any questions, I'll be here for another minute or two. So our groups are still going to be part of the more reactive. It's just they're going to be like super weak. What's up? Oh, thank you. I'm going to put this in my water bottle. Okay. Oh, so sweet. I really needed that today. What? So here. Here. Let me move this right. 77. Hell yeah, killed it. What? I don't want to. I just don't read my emails. For you, I will. Email me and I will. I can do that as well. Do you want just this or like all the stuff we all? Yeah. I'm just, yeah. I'm just gonna get out of my her way. Let's. Yeah. How would you want to be an L? I thought you said. Go ahead.